The relationship between the Earth and the Moon is a fascinating and complex story of gravitational forces, tidal interactions, and long-term changes in the dynamics of our planet and its natural satellite. To fully understand the Earth-Moon system and the future of the Moon, we need to explore the history, current state, and the processes involved in their interaction. The most widely accepted theory about the Moon's formation is the giant impact hypothesis. According to this theory, around 4.5 billion years ago, shortly after the formation of the solar system, a Mars-sized body, often referred to as Theia, collided with the early Earth. This colossal impact ejected a significant amount of material from Earth's outer layers into orbit. Over time, this debris coalesced under the force of gravity to form the Moon. Initially, the Moon was much closer to Earth, possibly just 10,000 to 20,000 kilometers away compared to the current average distance of about 384,400 kilometers. The proximity of the Moon had profound effects on Earth, including much stronger tidal forces, which would have caused intense volcanic activity and significantly affected the Earth's rotation. One of the most important aspects of the Earth-Moon system is the interaction through tidal forces. Tidal forces arise because the gravitational pull of the Moon is stronger on the side of the Earth that is closer to it and weaker on the far side. This differential gravitational force causes the Earth's oceans to bulge out in two directions, toward the Moon and away from it, leading to the phenomenon we know as tides. However, these tidal forces also have another critical effect. They cause a transfer of angular momentum between the Earth and the Moon. The Earth's rotation causes the tidal bulges to be carried slightly ahead of the Moon. The Moon's gravity acts on these bulges, pulling them back toward the Earth-Moon line. This creates a torque that slows down the Earth's rotation, and as the Earth loses rotational energy, this energy is transferred to the Moon, causing it to move to a higher orbit. Essentially, the Moon is slowly drifting away from the Earth. The Moon is currently receding from the Earth at an average rate of about 3.8 centimeters per year. This may seem insignificant on a human timescale, but over geological timescales, it adds up. Evidence from ancient records and geological studies supports the idea that the Moon has been drifting away for millions of years. For example, studies of fossilized tidal rhythms, called tidal rhythmites, show that around 900 million years ago, the Moon was significantly closer to Earth, and the length of a day on Earth was only about 18 hours. The Moon's gradual recession will continue for billions of years. As it drifts away, the Earth's rotation is slowing down, meaning that the length of a day will continue to increase. In the distant future, a day on Earth could be much longer than the current 24 hours. As the Moon moves farther away, its gravitational influence on Earth will diminish, leading to weaker tides. The difference between high and low tides will decrease, which could have significant effects on marine ecosystems. Interestingly, this process of the Moon drifting away won't continue indefinitely. In a few billion years, the Earth and the Moon will reach a state of mutual tidal locking. Tidal locking is the condition where an object's orbital period matches its rotational period. The Moon is already tidally locked with Earth, meaning the same side of the Moon always faces Earth. Eventually, Earth will also become tidally locked to the Moon. When this happens, the same side of Earth will always face the Moon, and the Moon will appear stationary in the sky from that hemisphere of Earth. This would mean that Earth's rotation period, a day, and the Moon's orbital period around Earth, a month, would be the same. Once tidal locking is achieved, the Moon will no longer drift away from Earth, as the transfer of angular momentum will have ceased. The system will have reached a state of equilibrium. Looking even further into the future, several factors could influence the ultimate fate of the Moon. In about 5 billion years, the Sun will exhaust the hydrogen in its core and enter the red giant phase of its life cycle. During this phase, the Sun will expand enormously, potentially engulfing the inner planets, including Earth and the Moon. If the Earth-Moon system survives the Sun's expansion, the intense solar radiation and stellar winds could strip away much of Earth's atmosphere, and both bodies would be subjected to extreme heating. Alternatively, the Earth and Moon could be engulfed by the expanding Sun, leading to their complete destruction. Although the Moon is slowly moving away, it's unlikely to escape Earth's gravity. For the Moon to escape Earth's gravitational pull entirely, it would need to reach a distance where Earth's gravitational influence is weak enough to be overcome by other forces, like the gravitational pull of the Sun. However, Current models suggest that the Moon will stabilize in its orbit long before it could ever reach this point. In summary, the Moon is drifting away from Earth at a rate of 3.8 centimeters per year due to tidal interactions that transfer angular momentum from the Earth's rotation to the Moon's orbit. Over billions of years, this will lead to longer days on Earth and weaker tides. Eventually, Earth will become tidally locked to the Moon, stabilizing the system and ending the Moon's drift. In the distant future, as the Sun enters its red giant phase, the fate of the Earth-Moon system remains uncertain. If it survives, the Moon will remain in orbit around a much-altered Earth. If not, both could be consumed by the Sun. The story of the Earth and Moon is one of gradual but profound change, shaped by the forces of gravity and the inexorable passage of time.